Good morning, everyone. I hope you are enjoying your snow day. The ideas that are presented in this screencast today are foundational to what we're going to be doing in the second semester. So you may want to read your textbook either immediately before or after this to help you understand the ideas that I'm going to present to you a little bit more. So the main idea of what we're going to be doing in the second semester is called statistical inference. We have a population of interest that we're trying to estimate something about that population, and so we take a sample. And from that sample, as long as it's a representative sample, so simple random sample, stratified random sample, not convenient sample, but as long as it's a representative sample, then that allows us to make an inference about the population. Think of it this way. You have a large pot of soup. Do you eat all, 2,000 spoonfuls of that soup to decide if it's good or not? No. You mix up the pot and then take a single spoonful and have that be a representative sample, and from that sample you make an inference about how the whole pot of soup would taste. So in order for us to understand sampling distributions and the other ideas that we're going to be talking about in this section, there's two key vocabulary words that you need to know. So you might want to grab a piece of paper and pencil and jot these down. First of all, a parameter is a number that describes some characteristic of the population. So it might be the true population mean, it might be the true population proportion, maybe the proportion of people that would vote for a particular candidate out of all possible voters. And then we have a statistic, which is something that we can gather and something that we can collect, something that we can figure out. And that's a number that describes some characteristic of the sample. Here's an easy way to remember the difference between statistics and parameters. Statistics come from samples, and parameters come from populations. Notice the first letters of these words. Here are some population parameters and sample statistics we've worked with in the past. Mu, the population mean. X bar, the sample mean. P, the population proportion, although some textbooks actually use the Greek letter pi. And P hat is the sample proportion. That's red P hat. Lowercase sigma, the population standard deviation, and S, the sample standard deviation. So you might want to pause the video here for a moment to see if you can solve these two problems. Let's identify the population parameter, sample, and statistic in each of the following settings. So in the first example, a pediatrician wants to know the 75th percentile for the distribution of heights of 10-year-old boys. So she takes a sample of 50 patients and calculates the third quartile for those 50 patients. Well, her population of interest is really all 10-year-old boys. And she really wants to know the 75th percentile for all 10-year-old boys. So the 10-year-old boys is the population. The parameter of interest is the true value for the 75th percentile. Her sample is the 50 patients, and from those 50 patients, she gets the statistic of 56 inches for the third quartile, which is the 75th percentile for that group of 50 patients. Population, parameter, sample, and statistic. Let's take a look at this next example. This was a study that was done in 2009, so I'm guessing this value might be a little bit higher here now. It says a Pew Research Center poll asked 1,102 12 to 17-year-olds in the United States if they have a cell phone. Of the respondents, 71% said yes. So let's assume for a moment that they asked all 1,102 and they actually got responses from all of them, although I'm guessing the response rate was not 100%. The true population of interest is all 12 to 17-year-olds in the United States. The parameter they're interested in is knowing what percentage of all of those 12 to 17-year-olds own a cell phone. So the true proportion who own a cell phone. Their sample is the 1,102 that responded. So the 1,102 12 to 17-year-olds in the U.S. that responded. And then the sample statistic is 71% said yes. This would be your P hat value. So our population is all 12 to 17-year-olds in the United States. Parameter will be P, the true proportion who own a cell phone. Our sample is the 1,102 12 to 17-year-olds in the U.S. who responded, and our statistic, our p hat value, would be the 71%. P hat equals 0.71. So one of the questions you may be asking is, how can a single value for a sample mean or a single population, a single sample proportion be an accurate estimate for a population parameter? How can a single value give us an estimate for a population parameter? Wouldn't some of our sample statistics be higher and some be lower? Well, that's true. We expect that. That's called sampling variability. If we take many, many different samples, we know that there's going to be variation from sample to sample. Think about the German tanks activity that you did. Did you get the same value every time you drew a sample of 7? Of course not. That would be silly. We sometimes got lower values and sometimes we got higher values. But sampling variability allows us to come up with estimates for our population mean and our population proportion. So let's take a look at the idea of a sampling distribution. This idea of a sampling distribution is somewhat hard to think about, but we'll see how it works in the next couple slides. So the idea of a sampling distribution is that we want to take all possible samples of size n and calculate the sample statistic from all of those samples. If we were then to plot all those values, we'd have a sampling distribution. So imagine the German tanks example that you did. You ran the simulation maybe 1,000 times or 5,000 times in Fathom, but if we were to take all different possible samples of size 7, ranging from maybe grabbing the first 7 tanks numbered 1 through 7, or the last 7 tanks that were numbered from, I forget what it was, 330 something to 344, and all combinations in between, if we were to take all different samples of size 7 and run our sample statistic with all different samples of size 7, plot all those sample statistic values, we'd have the true sampling distribution. One key here is that all those would have to be the same size. Meaning, in the German tanks activity, you'd have one sampling distribution if you use size 7. Your sampling distribution would be different if you use size 20, and we'll talk about that. So there's 3 different distributions that we need to think about here. The population distribution is the original distribution that we're trying to estimate the mean or the proportion for. Then we take one sample and we have a distribution for that sample. And then we have the sampling distribution, which is based on all possible samples of the same size from that population. This idea is somewhat hard to get around unless we have a picture to look at. So let's take a look at a picture. So here we have a population of 200 chips. I've got 100 that are blue and 100 that are red. So the true population proportion of red is 50%, 0.50. Now let's say we didn't know that 50% were red. What would we do? We would take a sample. So we take a simple random sample of size 20. So here's our population distribution. This is the truth. 50% red, 50% blue. I take a simple random sample. Did I get 50% red and 50% blue? No, I didn't. As a matter of fact, I got 40% red, 8 out of 20, or 40%. So from this sample, my p-hat value is 40%. Put the chips back in the bag, do another simple random sample of 20, and now I have a p-hat value of 55%, 11 out of 20 were red. And we would do this process again and again and again. Notice the 3 dots here, again and again and again. And if I had all possible samples of size 20, then I would have this as my sampling distribution. Notice where the center of my sampling distribution is, and notice that our true population proportion is 0.5. So one of the questions you might have is, how trustworthy is a statistic as an estimator of the parameter? For instance, back here, we might get estimates that are pretty accurate and close to the truth, but we might have ones that are off a bit, right? So how trustworthy is our estimate? Well, we're going to talk about shape, center, and spread here to get a complete answer to this question. So let's think back to the chip example here. Notice that our chip example, the red chips and blue chips, we knew the truth. We knew that there was 50% red. Notice where our sampling distribution is centered at. Our sampling distribution is centered at 0.50 or 50%, right? Because this is centered at the truth, this is called an unbiased estimator. Because the mean of this distribution is 0.5, the center of this distribution is 0.5, and the true value of the population proportion was 0.5, this is considered an unbiased estimator. Be careful not to confuse biased and unbiased from this section that we're talking about here, Chapter 7, Section 1, with biased and unbiased related to doing surveys. This is a totally different idea. This is an unbiased estimator if it's centered at the true value of the population proportion. But obviously low variability is better. There is quite a bit of variability back here, and it'd be nice to have lower variability. So lower variability is better. How do you think we could have a lower variability? If you said increase the sample size, you're correct. We'll talk about that in a little bit. So notice that using an unbiased estimator doesn't guarantee that the value of the statistic will be close to the actual parameter value. Here, notice we could be way off. 80%, 75% red, which is nowhere near the true population proportion of 50%. So we want to take a larger sample size. Notice here, if I have a sample size of 100, I have quite a bit of variability, whereas a sample size of 1,000 definitely reduces the variability. So larger samples have a clear advantage over smaller samples. And they're more likely to produce an estimate close to the true value of the parameter. So one of the things that we talk about also is variability of the statistic, in terms of describing the spread of the sampling distribution. How much spread we have in our sampling distribution is dependent mainly on the size of the sample. Larger samples have smaller spreads. Notice here there's a condition that we'll be talking about as long as the population is at least 10 times larger than the sample. Usually this isn't a problem because our populations are often fairly large, like all residents in Pennsylvania or all teenagers in the United States. All right, and the last concept that we need to talk about is bias, variability, and shape. So we can think of the true value of the population parameter as the bullseye on the target. So picture shooting arrows at the target, right? You shoot one arrow at the target, that's like going in and grabbing a sample and calculating a sample statistic. Where was that sample statistic? Was it close to the target? Well, let's do several arrows. Now when I shoot arrows at a target, this is usually what happens to me. I'm really nowhere near the center of the target, and I've got a lot of variability. A sample statistic like this would be bad at estimating the true value of the population parameter. We have high bias and high variability. What might be better? Well, low variability is better. However, this is nowhere near the center of the target either. This is also bad. This has high bias. It's nowhere near the center of the target, nowhere near the center of the true population parameter. This is a bit better. However, there's a lot of variability here. Yes, we're centered around the center of the target here, but we're quite a bit off in terms of variability. One of our arrows might be close, or we could be way off. We don't know which one it is. The ideal situation is to have no bias, so to have the center of our distribution, our sampling distribution, be centered at the true value of the population parameter, and to have low variability. So bias means that our aim is off. We want to have low bias, or in this case, no bias. And high variability means our results are widely scattered. We don't want that. We want low variability and no bias. Please be sure to read Chapter 7, Section 1 if you haven't already done so. And also do the Reese's Pieces activity that I mentioned in your handout. Actually, let me navigate away from this and find that website to show you what that looks like. Okay, so this is the activity that's in your textbook. It's from page 443. You're going to launch Reese's Pieces applet. It looks something like this. It's at the Rossman Chance website. And you can say Reese's Pieces here. I'm also going to be sending you a handout that has more specific directions related to this. But let's say that the probability of an orange candy is 50%, and let's say I take one sample of 25. So you can see the candy is coming out, and we've got some orange and some that are not orange. So here we had 11 out of the 25, right? And that's showing that as not as a percent, but as the actual number of orange. You can change this to proportion, and notice it changes it to a proportion. Right? We can draw many samples if we want. We might not want to animate that at that point. We might want to draw, let's say, 100 samples of size 25. Actually, let's do 99. That way we have a total of 100. Right? Notice the last sample proportion of orange was 56%, 0.56. Right? Notice the proportion of orange. This was a partial sampling distribution. And notice a normal distribution fits over this fairly well, and that might come in handy. So there's an activity with this that you're going to do, and you're going to take a look at what happens as you change different values here, and you change the sample size here as well. So I will be sending you a handout with that as well, so you can work through that, and then you don't have to go back and forth to your textbook. See you in class tomorrow.